Okay, hello, welcome to the video. And in this video, we will be talking some about some intuitions. And until now, we talked about the locations of the poles in terms of frequencies, and we derived the equations for our the location of our poles for our system, and which was something like um, some conductance in the numerator divided by some capacitance in the denominator. And we talked how it came. And now when it comes to develop the intuitions, let's review how one can tell the values of poles in a circuit intuitively. So let's take our opamp, and we know this is a transfer function, and by rearranging it, we can say that we have our pole over here. So our pole lies at minus G1 by C1. So when we cascade it with another amplifier for the sake of generating a current control voltage source, as we decided earlier. So at this point, the only missing capacitor over here is this one, and we said that over here um, we have, if we divide it into two different nodes, so we have transfer function for our first part and we have transfer function for our second part. And basically we can intuitively say that our first pole lies at this part where this portion gives us the pole, and our second pole lies at this part where this transfer function gives us the same result. And now let's try to relate the case where we had a circuit with C, for which we derived the pole values in our previous video. And let's take the circuit which is without C, and let's see what effect our circuit or our poles has when an extra capacitor C is involved between two nodes. And for this, we need a term called as Miller's theorem, or a Miller's compensation for a capacitor. So let's talk about it. And let's see, we have when we have a capacitor C between two nodes of two stages, our pole 1 lies at this frequency, and without C, we say that our pole lies over here. So and this is with a minus sign of as it is a left hand part pole. Now we can see when it was without C case. So we had basically G01 by C1, and when C was there in our circuit, so we have the term G01 in the numerator as it is. We also have C1 in our denominator, but few extra things were added in the denominator, which are basically coming from the extra capacitance due to Miller's theorem. So what is Miller's theorem? So basically, when we say that at our input and at our output of any transconductor, there is a capacitor linked. So let's say the gain of this transconductor is minus Gm2 upon Go2. So this is basically a transconductor with C in its feedback. So it simply, we can, like Miller theorem simply states, that we can redraw this circuit in this manner, where at the input stage we can consider a capacitor instead of across it. We can consider it at input end, and we can say that the value of that capacitor is gain times plus 1 multiplied by C. So this is our gain, which is Gm2 by Go2, and plus 1 times the capacitor C. So this is the value of capacitor we can consider at the input. And this is some kind of Miller's theorem. And in our case, in stage 2, so basically like we know from Miller's theorem that if we are using an amplifier of with a feedback of capacitance C, so and V test is applied at its input, so we can say that if we are applying V test at its input, then we can um, consider a capacitor whose value is A plus 1 times C, where A is gain of the amplifier. And there are also few other, like due to this, we have this term which is basically gain plus 1 times C. And where did this term came from, or this term came from? So basically there are also few other terms due to the reason the pole was obtained approximately, and the op-amp is not ideal. So but it turns as that like turns out that the highlighted terms are significant, which are basically this one. This is from the Miller compensation and this term. So basically, we can relate our intuition with our actual value. And basically, we can say that in this case with C, the denominator like denominator has increased a lot, and which states that the pole moves to the lower frequency. So when there was a case without C, so let's say the pole was at GO1 by C1, now the denominator values are increased, and as the weight of denominator increased, the pole P1 has shifted towards lower value. So this we can state. And when we talk about P2, so without C, the pole lies at minus GO2 by CL. And when we have a case with C across the two nodes, so we have somewhat this kind of a value which we derived in last video. And we can say that we can compare two equations, and we can say that we have GO2 in the numerator, Cl in the denominator, but there are also few terms extra in denominator as well as in numerator. So we know that poles are the characteristics of a circuit, and they have nothing to do where the input is applied. So hence we can examine the circuit without zero input, and our circuit with zero input will somewhat look like this, where our first stage is basically of no use as there is no input, and our second stage will also look like this. And over here, what is the capacitance associated with this node? So this is our question. So originally we had only GO2 and Cl, but now we have some capacited like we have some capacitance which is somewhat complicated, and which is basically Cl parallel to some capacitance which is C in series with C1. So we have C in series with C1, and which is parallel with Cl. So basically the total capacitance will become somewhat Cl plus the voltage divider, we can say CC1 upon C plus C1. So this is where the term comes CC1 divided by C plus C1. And we can also say that we also have some conductance terms in the numerator, and those are this and this. So basically when we consider our second stage, so if we apply voltage V at the output end, and then due to capacitive network, um, at this point the voltage will be nothing but due to the voltage divider of these two capacitors, and that voltage will be C divided by C plus C1 times V. So the current flowing is basically Gm times the voltage, which is C divided by C plus C1 times V, and this is the total transconductance which we are getting. And basically when we look our numerator term, so this is the same transconductance which is a term getting added in the numerator. And we also have GO1 before this C1. So before this C1, we also have GO1 over here, and the numerator has drastically increased as compared to the case without C. So let's see how. But before that, due to this GO1 present which is presented here, basically this term appears. So now we can see the numerator is basically increased. The weight of numerator is increased as compared to the one we originally took. So this simply can state that the pole shifts to the higher frequency. So this is a phenomena where we can say while applying intuitions that both poles go apart from each other, and this is called pole splitting, where P1 moves to the lower frequency and P2 moves to the higher frequency when there is a capacitance between two nodes of our second stage. So this is the case without capacitors, but where we when we apply a capacitor over here, and so this is the case where we can experience pole splitting. So now summarizing the two-stage op-amp from the single-stage op-amp. So as we know, both have the omega u, which is basically equals to GM1 divided by C. And at a single stage, the first pole P1 lied at minus GO1 by C. And when we had two-stage op-amp, so our first pole basically lied at this frequency, which is intuitively derived, and our P2 lied at this frequency, and there is also one zero associated which lied at GM2 by C. So let's plot a Bode plot of our second stage op-amp. So basically it will go at its DC gain, which is GM1 GM2 upon GO1 GO2, and then it will have its minus 20 dB per decade slope at pole P1, and when it will reach at unity gain frequency at 0 dB point, that is our omega u, or unity gain frequency. And after that, at point P2, we will have more decrease, which is minus 40 dB per decade, and then again we will have a zero, and which is present in right hand plane. So again we will have minus 20 dB decrease. So minus 20 dB per decade, minus 40 dB per decade, and due to a zero in right hand plane, again minus 20 dB per decade. So here we have assumed that P2 is P2 is at lesser frequency than the zero. So now at the point of omega u, where the first order curve touches the 0 dB line, due to its minus 20 dB per decade first order behavior, we can say that omega loop is equals to omega u, where the k value is 1. So the k of this loop is 1, and which is basically gain times P1, because this is the gain and this is our P1, and due to the curve characteristic, we can say that omega u is basically the gain times P1, the magnitude of P1. So if we put the values of gain and if we put the values of P1, so basically GM2 by GO2 plus 1 is nothing but GM2 by GO2, because it is very large as compared to 1, and as C times GM2 by GO2 plus 1 is very greater than C1, so C1 can be neglected, and thus from here we neglect the C1, and basically this term is GM2 by GO2 only, and this is cancelled by this term, and this GO1 is cancelled by this term. So basically we are left with GM1 by C. So that is how we consider our omega loop anyway. So we are arrived at the right equation. And now in the case of resistive load for second stage, so if we have a resistive load, then our gain becomes GM1 GM2 divided by GO1 times GO2 plus GL, And in our first, like in the case of our one stage op amp, the gain is basically gm1 by go1 plus gl. So what we are basically stating that if we have our resistive load over here at our output, so basically our equations will change for the gain, and basically that RL is parallel to our other circuit. So we have to consider that parallel resistor over here, which is in the form of conductance GL, and this is how we consider the parallel resistive load in our equations for our gain. And now when we write it in for the case of resistive load, so we can clearly say that due to this resistive load, the gain is limited over here in a single stage op amp. And if we increase too much of gm to compensate it, then we face issue with the power dissipation, and obviously we need a higher gain. So this is an issue with single stage op amp. But when we come to our two-stage op-amp. So in this case, even if the gain, like even if this whole term is limited due to GL, but we also have GM1 by GO1, and we can say that GM2 contributes less due to the resistive load, but GM1 is so sufficient high, like it's sufficient high enough, and like we don't have to compensate the gain, as first stage is isolated from the load. So and our gm1 from first stage is actually anyway high. So this is the advantage of second stage op-amp over first stage op-amp. So now let's come to stability. And when we talk about stability, so we have a transfer function of an op-amp, so which is basically our ideal gain, and along with that we have our zeros and poles. So this is our zeros and these are our poles. So stability margins, like stability or phase margins or etc., are determined by loop gain, and the loop gain itself depends on the feedback loop that we placed the op-amp in. So let's realize op-amp with gain k. So this is the feedback loop with a gain k, and we know that a of s is our transfer function, and l of s is basically our loop gain, and which is nothing but our dc gain by k. So loop gain depends upon the value of k. And now let's say we put this op-amp in negative feedback loop with k equals to 1. So this is the worst case anyway. We'll see further how, we'll see later how k equals to 1 is a worst case. But as of now, let's say that if k equals to 1, then our omega loop becomes omega u by 1, which is basically omega u, and our loop gain, so this is our loop frequency omega u, which is omega u, and our loop gain is basically our dc gain a naught. So now if you plot a Bode plot, so for our a naught, when our loop gain is a naught and value of k is 1, this is where we can see our curve in blue line, and this is where our p1 lies, this is where our p2 lies, and this is where our 0 lies. So, and we know the rules of Bode plot. So now this is the function of, this is the transfer function of our op-amp. But here one thing we have to notice, that we have considered k equals to 1. What if the value of k is higher? So if the value of k is higher, then our loop gain reduces, and let's say its value is a naught divided by k. And for higher k's, the more higher k it is, the curve is more towards the origin, we can say. So now this is how our curve will look, and the unity gain bandwidth will shift towards origin. So firstly it was here, now it will be here. So as we increase the value of k, our unity gain bandwidth close to the left hand side. So the phase margin is how, like let's talk about phase margin. So basically the phase margin is how far is the phase from 180 degrees, basically minus 180 degrees, when our loop gain, magnitude of our loop gain is 1. So when we plot our phase, so at P1 we will get minus 90 degrees phase shift. At P2 we'll again get minus 90 degree of phase shift, but again a zero arrives, which is again a right half plane zero. So it will give more decrease in our phase, and then it will get constant. So this is how our phase will look. So we have the highest phase lag for k equals to 1, because when k equals to 1 we have the highest value of omega u. And at this point, let's say for k equals to 1, and this is the point where we can say that we have highest phase lag, and which is for k equals to 1, means it is nearest from pi, and that's why it is the worst case. So like, this is relevant when we design an op-amp without any information on k. We simply have to assume some value of k. Obviously we will assume the worst case, and we'll consider it when k equals to 1. So now let's say that we have to design an op-amp for the worst case, which is basically k equals to 1, and our phase margin should be 60 degrees. And let's say when our k will be equal to 1, our omega loop will be basically nothing but omega u, and our loop gain is a of s. So now here we can say that a of s is written like this, and the phase is given by minus tan inverse of omega by z1 minus tan inverse of omega by p1 minus tan inverse of omega by p2, where omega is basically nothing but omega loop, which is nothing but omega u. So now we have plot our function, transfer function, and we know that this is our loop gain function, and basically which is basically a naught. So we will have our DC value, and then we will have the curve accordingly. We have discussed about the curve, and over here when our this is how our phase looks, and we need the phase margin, which is basically 60 degrees at omega u. So let's say we have the equation for our phase, which is nothing but pi plus this value. So this is the value, and now let's take each and every term, and let's decode it. So tan inverse omega loop by z1 is basically the value of omega loop is gm1 by c, and the value of z is gm2 by c. So basically omega loop by z1 is nothing but gm1 by gm2. Similarly, let's take this part. So omega loop divided by magnitude of p1 is nothing but a naught, as a naught is a very large number. So we can say that tan inverse of a naught, basically tan inverse of very large number, is nearly about 90 degrees. So we can say that this part gives us the phase lag of 90 degrees. Now we'll keep this part as it is, because we have P2 at some complicated frequency and complicated equation, and then we will get our phase margin equation like this. And now let's say we have the requirement of 60 degree phase margin. This 90 degree will separate it out, and in bracket we have two tan inverse terms, basically tan inverse gm1 by gm2 and tan inverse omega loop by p2. So this means only this part has to be of sum of 30 degrees, as 60 degrees is basically 90 minus 30 degrees. So sum of these two parts should be 30 degrees, and we know gm1 and gm1 by gm2 is basically high value. So we have to consider these two terms, and the summation should be 30 degrees, and 30 degrees itself is a very small number tan inverse can have. So we have to limit the values, and from this term, we can say that gm2 must be made higher than gm1. So we have to make gm of second stage higher, much higher than gm of the first stage, in order to limit the tan inverse term. So let's say gm2 is made 4 times of gm1. Let's take an example that by design we will take gm2 4 times of gm1, and that's how we will get tan inverse of 1 upon 4, which is basically 14 degrees. And from here we can say that we need now this term to be 16 degrees. So now let's say this term will put the values, and we need this term to be 16 degrees. So tan 16 will become this term, and we have done nothing but we have put the value of omega 2 and p2 in our equation. This is our omega loop value, and this is where our p2 lies. So this gives us a quadratic equation in C, and we can, after again resolving a little bit, we will get this equation. And for given values of, like, let's decode this equation more and write it in a quadratic equation in C by CL. So this is how our quadratic equation will look like. And for the given values of gm1, gm2, cl, c1, we can easily find C. And this intuitively makes sense to normalize C by CL, because for larger values of CL, omega loop for second stage, basically for our current control voltage source, tends to be small, and which is what we want. So it makes sense to normalize the C value by CL. So now again, so this is for our P1. Now let's this is how we design for our case where we have the given K and phase margin. So, but we are getting a quadratic equation, and solving this quadratic equation is little bit tough of a task. So for our intuitions, we will discuss what is first cut approximation. And as of now, let's consider that we know our P2 lies at somewhat this complicated frequency. So let's take a case for our first cut approximation where C is very, very larger than C1. So basically C plus C1 is nothing but C. So now our equation will break down to this value when we consider C is very, very greater than C1. And does this make an intuitive sense? So we will see. So now in this feedback over here, due to C and C1, there was a voltage divider. Due to C1 and C, at this node, there was a voltage divider. But now, as we know, C is very, very greater than C1. So this voltage divider is nothing but C1. So basically there is no voltage divider, and this acts as short circuit, where any voltage at this point appears at this point. So basically this is short circuit. And now the second stage will look somewhat like this, where we have a short and we have its gm2 value. So if transconductor is shorted on itself, then the transconductance will be gm2 itself, or a resistor of, it will act as a resistor of gm2. So basically it is shorted on itself, so it will act as a resistor, and which has a conductance of gm2. So it will act like this. So basically our circuit will look somewhat like this, and this is due to our transconductor. So now the pole P2 comes at this value, as we decided, like we saw over here, and this is our first cut approximation. So intuitively, we said that our P2 will come over here from this case and from this equation. And here we, from our circuit, intuitively we derived that our pole P2 will come at some transconductance, which is total transconductance, and some capacitance associated at this node, which is C1 plus CL. And this is our first cut approximation. And thus, tan inverse omega loop by P2 was 16 degrees. And we can say now from our intuition that this is equals to 16 degrees, and which gives us a linear equation in C, and which simplifies our problem of solving quadratic equation in C by CL square. So this is how we solved the problem of a complicated quadratic equation by simply considering a intuitive case. And I think that's it for today's video. Thank you for watching.